That's all right. All right, here we go. So in a reaction, the substance from start to end chemically, yes, I agree with you. That changes. That changes. Excellent. Beautiful. No worries. That's all right. All right, so looking over here, the ending substance in A reactions are called the products. Good. Yeah, that's exactly what they are. And finally, let's go up to here on endo and exothermic reactions. In the exothermic reaction, heat exits. Again, kind of look at the first two letters. It's kind of our dead giveaway here. Exo, exits, okay, EX, EX, they match together. In an endothermic reaction, heat enters. Same idea. Look at the first two letters. Enters begins with the first two letters of endo. So again, little hints there to help you out. Awesome job, everybody. If you could have any car, what would you have? OMG, a Subaru Forester, a Honda CRV, both CRVs are SUVs. I like that. Nice. And fuel economy too. That is a good one. Miles, you are thinking. A 1998 Toyota 4Runner. That is super cool. Let's see who that was. Is that Miles too? Maybe it was Miles. I can't read. Miles too. I do not, it's kind of funny. That's the only car I get car sick in. I can read, I can do computer work, I can do anything, but for some reason, the Toyota 4Runner is the only car I get car sick in. I think it's the small front window because it's for off-roading, so it's like that small front. I don't know. I think I'm just nuts. I don't know about cars, but as long as it works, I like that one. Nice one. Let's see who that was. Excellent. I like that one. Unless it's driving. Mrs. Larkin is a car sick person. Oh no, no, I could read, I could do all sorts of different stuff in the car. But for forerunners, I have to I have the windows down. Like I don't know what it is. I think it's crazy. Honda Civic Type R for sure. Love that, Steven. Mine be with truck, a diesel truck. Anthony, yeah, that's my husband's. He's actually in the market right now for a truck, so that's what he's looking at. Um, I like, one car I really liked, and obviously very expensive and fuel economy is terrible, but I loved my Yukon XL. I had a Yukon XL and I had no kids. I just had a dog and I had this big car and I was just like, yeah, like big, Big Bertha just, rah. It was crazy. Um, yeah, yeah. So, but I went to a more fuel economy car. So, all right, let's go ahead and move on. We could talk about cars all day long. Let's talk about what we need to be doing today. Remember, Class Connect sessions are recorded and distributed for learning purposes. Please do not put any personal information or information of others into the chat box for your protection and the protection of others. Make sure you're participating and make sure you're respectful and school appropriate. All right, we have our attendance. Here we go. I am seeing some hands raise up for our attendance. Get your attendance in. There is our two links. Again, one of them is going to work. If you're unsure which teacher you have, try both of them. One of them is going to work. Make sure you get that attendance word in. It's a tricky one today. Make sure you're spelling it correctly. We are going to give you the first 15 minutes of class to get that done. Obviously, you do technically have until midnight tonight to get that in. Just copy the word down, make sure you're spelling it correctly, and get it in if you're going to do it later. I do want to see some hand raises, so hurry, hurry. Let's get some hand raises. I'm only going to give you about, let's see, maybe 20 seconds. Yeah, okay, there we go. I pushed the button, so go, go, go. 2 seconds. Oh, man. Eric, I don't like to see that. I'm frozen. That's not fair. All right, here we go. So let's take a look. Timothy, Tim, Aria, Michael. We're moving. Kale, Kamari, Omar, go ahead and raise your hands. Thank you, Gabriel. Good morning, by the way. Aria, Michael, Kale, Kamari, and Omar. Let's raise our hands. I will be checking in with some of you. And good morning, Adriana. We are doing our attendance. Please raise your hands. Hurry, hurry, hurry. Thank you so much. I will be checking in with a few of you. All right, today, it looks like Miss Larkin, do you want to do this one?
Yeah, I'll go for it. So today we are going to go ahead and take a look at balancing chemical equations. I did just want to reiterate again that we are doing notes for these 3 days, and these notes do go into your project part of your gradebook. So they do help to boost your grades. Keep in mind that we will be zeroing out the Unit 3 project soon. So if you haven't yet done that, make sure you get that in as well, because obviously your grade's going to tank if we don't have that turned in. You'll have to get it turned in a little bit later in order to see your grade go back up. But again, notes are a really good way to add a little bit of extra extra to your project section of your gradebook. So make sure you get that done. And then don't forget, we will be starting our newest project on Thursday, taking a look at amazing reactions, some of which we've already seen. We'll be taking a look at those more on Thursday as we start our newest project.
Discuss what we're going to be doing today. We're going to talk about reactants, products, and coefficients in a chemical equation, and we're going to balance a chemical equation. Fun stuff here. So this is all in our 4B notes, more than 80% of higher. I know you all be doing that. So with that, here we go. Let's open up our notes. We're going to put those notes inside your the chat box there. There they go. They're going in. And again, remember that if, depending on which teacher you have, there you go, Mrs. Larkins, and then mine will be popping up. Again, if you're unsure, try both of them, but one of them will pop up. Obviously, when you have done that, go ahead and start your quiz. Raise your hand if you are watching the recording. Click the grades tab, scroll down to 4B notes, and start your quiz. Go, go, go. I'm going to give you about 20 seconds to do that. Let's get 100% in participation. My friends, seconds, 3, 2, 1. All right. Oh, we're moving. Sorry. Monty, Tim, Kamari, Christopher, Omar. Thank you, Casimir. Ignacio, Adriana, Tayan. Oh, hush. And Gabriel. Gabriel, Tayan, Adriana, Ignacio, Omar, Christopher, and Kamari. Let's get our hands raised. Hands raised, please. Quickly. We do have a lot to go through today. The last three, Kamari, Christopher, Adriana. All right, I'm going to go ahead and move on. Thank you so much.
All right, looking good, everybody. So yesterday we talked a little bit about chemical reactions. We talked about reactants are what we start with because reactants undergo the reaction. And we talked about products, which are what we end with. Remember, products are what get produced, right? So that's how you can remember the difference between those. Reactants go on the left, products go on the right. And we are going to go ahead and continue learning about chemical equations. So chemical equations, we mentioned, will represent what we start with and what we end with, but they will also tell us exactly what's going on exactly how much of the reactants we need and how much of the products we will produce. So this will kind of be like our recipe that tells us exactly how much of everything that we need. Now, chemical equations are also pretty cool because not that we talk too much about this during our chemistry class, but you might learn this in the future. But there are kind of these rules or data that we already know that will help us predict from a chemical equation whether or not a reaction will even actually happen. So for example, you can see here that copper, this metal right here, will react with nitric acid, which starts out as a clear liquid. But aluminum, you can see, is not reacting with nitric acid. Tell me in the chat box, what is some evidence that you see here on the left-hand side that shows you that there's probably a reaction happening? What do you observe about the left-hand side that's different than the right that is indicating there's probably a chemical reaction occurring? Excellent. I see Shelbs in the chat box. Give me some more answers there. Let's be a little bit specific. Can other students tell me about what colors they're seeing? What are you seeing? There you go. Yeah, so we can see some bubbles. That might be hot, right? Those bubbles might be hot. It might be an exothermic reaction. Again, exo means it's giving off heat. Heat's exiting. It feels hot. Yeah, so we can see very vibrant colors. What colors do you see? What colors do we see? Let's be specific. Again, nitric acid starts out clear, and now it's turning what color? Yeah, we can see blue from the nitric acid, and you can also see bubbles are evidence of gas, and we can actually see the gas here, and that gas is a reddish, orange, brownish gas. So anytime we have gases being formed, and we can see that from bubbles or from the actual gas, or we see color changes, oftentimes that's an indicator that there's a chemical change going on. Again, the chemicals at the end are now different than the chemicals at the beginning. Not always. Sometimes you can still have color changes, or you can still have bubbling even when it's not a chemical change, but usually that's a pretty good indicator. All right, this is going to be number 1 in your notes. Go ahead and fill in the blank with the word equations. Make sure you spell it correctly. Make sure you only include the word equations. You have 20 seconds to get that in. Some of you are on your second or third check-in, so make sure you're checking in with us. 20 seconds, go, go, go. Raise your hands. All right, let's take a look here. Gabriel, Adriana, Gabriel in the chat. Let's get Casimir. Omar, thank you, Casimir, Kamari, Michael, Patrick, Aria, Monty. Go ahead and raise your hand or send us a chat if you are here and participating. Again, you get 3 chances, and then we will excuse you if we do not hear from you. Awesome. Thank you, Gabriel. I see you in the chat. All right, just waiting on Michael, waiting on Kamari and Omar. Please raise your hands if you're good. Michael, 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 Kamari, 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 Omar, Omar, Omar. Omar, 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 sorry. Please raise your hands. All right, looking good. I'm going to go ahead and move on here. Again, you get 3 chances to respond. AQ stands for aqueous. Stephen, aqueous, kind of like the word coming from aqua, which is like water. So aqueous just means that it is in a solution. It's in a liquid form. It's in water. So ammonia dissolved in water, hydrochloric acid dissolved in water. All right, looking good, everyone. Great question. So let's go ahead and take a look here. We are going to go ahead and start off with water because water is one of our most famous examples of chemicals in our class. So hydrogen and oxygen will react in order to form H2O, the chemical formula of water, but specifically hydrogen and oxygen actually exist as what we call diatomic molecules. Now, di means a certain number of atoms. Let's take a look at hydrogen. How many hydrogens are in this molecule? H2 tells us how many hydrogens are in here. Tell me in the chat box. That little subscript means how many hydrogens? Yeah, it means 2. Same thing with oxygen. That little 2 means there are actually 2 oxygens in a naturally existing O2 molecule. So in real life, hydrogen, oxygen, bromine, iodine, chlorine, fluorine, a lot of these atoms don't exist by themselves. They actually exist in diatomic, meaning kind of paired up molecules. So 2 atom molecules, that's what di means, kind of like carbon dioxide means there's 2 oxygens in dioxide, okay? So you can see I put the reactants on the left, H2 and O2 right here. I put the H2O on the right. That is the product. H2O is our water. And the arrow again shows that there is in fact a reaction happening. But today the question is the reaction balanced? All right, so we know a little bit about how to figure out what the recipe, the equation looks like. But the next question is it actually balanced? Because the problem is we need to have the same amount of each atom on the left as on the right, because we need to start off with the same amount of hydrogen and oxygen that we end with. We need the same amount of hydrogen and oxygen that we end with, because if for some reason we end up with more hydrogen or suddenly less oxygen, then that means that we are somehow deleting matter from the universe, or we are creating matter in the universe, which is impossible. That breaks the laws of physics. Conservation of mass says that we have to have the same amount of atoms at the start as at the end. Smiley faces, emojis if you understand. Smiley faces, emojis if you understand. Smiley faces, emojis if that makes sense. We have to have the same amount of hydrogen and oxygen. Cool. So what we're going to go ahead and do is we are going to go ahead and learn how to draw out equations. So when I draw out an equation, I don't want any numbers. I want to actually write out the entire letters. So instead of writing it as H2, I'm going to write it as 2 H's. So I'm going to write it as HH. I'm just going to write it out completely. HH. How do you think I can write out O2 completely? In the chat box, how do I write out O2 completely? O2 completely. If H2 becomes HH, what does O2 become? Yeah, exactly, Shelbs, exactly, Annabelle. It becomes O, 2 O's. So again, yeah, Gabriel, no numbers. Now we're just writing out every atom in there. So if there are 2 O's, I write O, O. Okay? Cool. Now let's go ahead and try out H2O. Again, the 2 here is attached to the hydrogen. The O has no subscript, which actually counts as 1. So go ahead and figure out how would I write that out completely. Instead of any numbers, write out all the atoms. Excellent. I see Maylin working. Again, even if you weren't sure, get it in now because this is your practice. You will need to be able to do this on your own for the last question. Yeah, okay, so yeah, be careful, Shelbs. Remember that O, actually, there should only be 1 because there was no subscript. That actually just counts as 1 oxygen. So HHO would be the most accurate one here. Perfect. All right, now let's go ahead and count up the individual atoms. So what you're going to see here is we're going to see circles today, and we're going to see individual letters today. They are different things. A circle counts as a whole molecule, like a whole molecule of H2, a whole molecule of O2, and a whole molecule of H2O. But we said when we balance, we want to focus on the individual atoms, which are going to be the little letters. All right, so taking a look here, how many hydrogens do you see on the reactant side, on the left side? How many individual little letters, little atoms of hydrogen do you see on the left? Individual ones. Take a look here. On just the left, ignore the right-hand side. We're only looking at the reactant side, the left side. There we go. Yeah, we actually should only see what two. Here's one, here's two. So two on the left, all right? And how many oxygens do you see on the left-hand reactant side? Yeah, also two, right? So one, one, two. So two oxygens on the left. What about on the right-hand side? How many hydrogens do you see on the product side? The product side. Yes, you should see two, exactly. And how many oxygens do you see on the right-hand product side? Yes, yeah, careful here. There's actually only one. So taking a look here, is this balanced? Do we have the same atoms on the left as on the right? Are we ending with the same amount of ingredients we started with? Yes or no? No, so this is a big problem because somehow we magically deleted an oxygen from the universe, which doesn't work. That's not how the universe works. You can't just magically delete matter or magically create matter. So somehow we need to fix this recipe. We need to fix this recipe, which is what we're going to go ahead and take a look at today. But before we get into that, I do want you to commit this vocab word to memory, so let's get that into our notes. Fill in the blank with the word diatomic, meaning a two-atom molecule. Only put in the word diatomic and make sure you spell it correctly. You have 20 seconds to raise your hands and let us know that you're ready to move on. 10 seconds remaining. Raise your hands. Raise your hands. Thank you, Gabriel. Excellent. I'm waiting on Tim, Tim, Tim. Waiting on Aria, Aria, Michael, Michael, Kale, Kale, Omar, 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 Adriana, Adriana, Tayan, Tayan, Ame, Ame, Jaden, Jaden, Dion, you just joined us. I'm going to go ahead and send out your attendance one more time, and then I will be deleting the chat box. So there's your attendance links. Here's the start of class word. And then I'll send out the notes as well. All right, so here's the notes from my class and the notes from Mrs. Sepulveda's, and I need hands raised for number 2 in your notes. All right, waiting on Kamari, Kamari, Kamari. Last chance, Kamari. Omar, Omar, Omar. I think this is your second or last chance, Omar. Go ahead and raise your hands or check in with us. Thank you, Omar. Perfect. And then Dion, Dion, please raise your hand if you got your notes open. Dion, Dion, Dion. Perfect. All right, let's go ahead and keep on moving. All right, looks like Kamari is the only one we haven't heard back from. Let's go ahead and keep on going. All right, so now we're going to learn about how do we actually balance chemical equations. So we can balance chemical equations using what are called coefficients. And these are going to be big numbers that we've put in front of each molecule in our equation to tell us how many of those molecules do we need. Now again, the number of molecules doesn't matter. We can change that, which is nice because as we figure out the number of molecules we need, that will make sure that our individual atoms on the left are balanced with the individual atoms on the right. So again, we don't have to balance anything with molecules, we need to balance atoms, and then the molecules can change to make sure that the atoms are balanced. Smiley faces, emojis, if that makes sense. So molecules are those big circles. Those can change, that's totally fine. The thing we need to focus on is the individual letters or atoms are balanced. Smiley faces, emojis, if you feel comfortable with that. You'll see what I mean as we practice this several times. Again, make sure you're practicing along with us because you will need to be able to do the last one on your own. Now, as always, remember that if something is blank, there's no number, that just counts as 1. So a subscript with no number counts as 1, and a coefficient with no number counts as 1, because anything times 1 is still itself, so it's a little bit redundant to write an extra 1. All right, so this is like saying, instead of me just being like, here, please bake a cake, you have butter, sugar, flour, and eggs, you're going to be like, Mrs. Larkin, I can't make a cake because I don't know how much of everything I need. This is like me actually giving you the ingredient list and the amounts. So 1 cup of butter, 2 cups of sugar, 3 cups of flour, 4 eggs. That was our example from yesterday. And so I could actually write this as an equation. Again, I leave this part blank because this just counts as 1. So 1 cup of butter. You can see 2 cups of sugar, 3 cups of flour, 4 eggs, and again, this blank right here counts as 1 cake. All right? Yeah, there you go. Sorry, that's a terrible one. Oh my gosh, 1 cake. All right, so again, these coefficients will help us to balance these equations, balance our recipe. Okay, so go ahead and fill in number 3, and then we're going to go ahead and actually fix our water example. You have 40 seconds to fill this in. First blank is coefficients, second blank is atoms. Make sure you only put in what you see in the red box, and make sure you spell it correctly. Go, 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 raise your hands. Yeah. All right, we're waiting on raised hands from Bryce, 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 Timothy, Timothy, Arya, Arya, Patrick, Patrick. Let's see here. Omar, 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 Casimir, Casimir, Kamari. Okay, no worries, Bryce. Shelbs, make sure you leave your hands raised. Raise your hand and leave it raised. Um, okay, give me a moment. Perfect. All right, Shelbs, Gabriel, Jaden. Shelbs, Gabriel, Jaden. Hello, hello. Wait, Gabriel, you might be in the chat. Yeah, you're good, Gabriel. All right, Shelbs and Jaden. Shelbs and okay, no worries, Shelbs. Just yeah, go into the chat. You're good. And Jaden, you're the only one we're waiting on. Jaden, Jaden, Jaden. Hello, hello. You get 3 chances to respond. Let's go. All right, I'm going to go ahead and move on, but we will be checking in with you. All right, so let's go ahead and actually fix our equation. So this is, again, what we started with. H2, we write out completely as HH. O2, we write out completely as OO. H2O has two H's, one O, so we write it out completely as HHO, and we counted up the number of H's and oxygens on each side. So let's go ahead and take a look here. What do we need to fix? Do we need to fix hydrogen or oxygen? Do we need to fix hydrogen or oxygen? We can't subtract. Okay, we'll go over why we can't subtract in just a moment, but what do we need to fix? Yeah, we need to actually go ahead and fix oxygen, all right? Now, which side needs more oxygen? The left side, our reactants, or the right side, our products? Which side needs more oxygen? Yes, the right side needs more oxygen. Now, in order to add more oxygen, you can't just add random O's, all right? I can't just be like, all right, let me start adding some oxygens over here. That would be like if I had a cake recipe and I magically started producing pies next to my cake. That does not make sense, all right? So we can only add more of what we have. If we have a cake, I can only add more cakes as our product. So in this case, I only have H2O, so I can only add more H2O. Smiley faces, emojis, if that makes sense. All right, I can't add oxygens by themselves. I can only add more H2O here, HHO. Cool beans. All right, so let's recount then. Now, how many hydrogens in total, individual letters of hydrogen, do you see on the right? How many hydrogen atoms do you see? Count up all of them on the right, on the product side. Nope, there's not two. Count up all the hydrogens, all of them, from all of the molecules on the right. Yeah, there are 4. Perfect. And let's count up the oxygens now. How many oxygens do we see on the products? Yes, there we go. 1 on the top, 1 on the bottom, so that counts as 2 oxygens right here. Cool. So now our oxygens are balanced. Is our overall equation balanced? Yes or no? Are we overall balanced? No. Now we need to go ahead and fix the hydrogens because we messed our hydrogens up. That happens all the time. Which side needs more hydrogen? The left side reactants or the right side products? Left side reactants or right side products? Which side needs more hydrogen? Cool. All right. Yes, you're right. The left side needs more hydrogen. Now, again, I can't just add random H's into this equation. I can only add more of what I have. So if I need more hydrogen on the left, what should I add another molecule of? Do I add another molecule of H2 or O2? What will give me more hydrogen on the left, H2 or O2? Which thing has hydrogen in it? Thank you. I see Annabelle in the chat box. I see Maylin in the chat box. Make sure you're capitalizing correctly because little h's are different than big H's. Yeah, exactly. So the only thing that has hydrogen in it is this H2. So I'm going to add another H2. If I added another O2, that would not help me because there's no hydrogen in O2, and I said I needed more hydrogen. So here's another H2. HH, all right? Again, can't add individual H's, have to add a whole molecule of H2. How many hydrogens do we now see on the left? Individual hydrogen letters overall on the left. How many do you see? Yes, we see 4. So now, are the atoms balanced? The individual atoms, are they balanced? Yes or no? Yes, they are perfectly balanced. This looks great, but we're not yet done because now we need to go back and fix the equation, the recipe, okay? And the way we do this, again, is based on coefficients, all right? So the way I'm going to do this is now I'm going to go ahead and look at the coefficients, which come from the big whole molecule. So when I'm counting coefficients, I'm going to count up the big circles, the big molecules of H2, the big molecules of O2, and the big molecules of H2O. Ignacio, just go to the Q&A area. Those are private. All right. So taking a look here, H2, okay, how many big molecules of H2 do I see here? All right, count up the big circles. Nope, not the individual letters. The big circles of H2. Big circles, not the individual letters. Yeah, you should see 2 big circles of H2. Here's 1. All right, and here's 2. Smiley faces if you can see that. Again, there are 2 big circles of H2. Here's 1. Here's 2. Okay, perfect. So that becomes our first coefficient. So 2 big circles of H2 it tells me I need two H2s. That would give me an HH, and an HH which would give me four H's overall. You might notice that this is actually multiplication. 2 times 2 would give me four H's. Okay, but you don't have to worry about it. That's why we do the diagram in case you're not as strong with multiplication. We get it. Now let's go ahead and count up the number of O2s we see. How many big circles, molecules of O2 do you see? Just one, exactly. Do I need a coefficient if we just have one big circle or molecule of O2? No, because remember, again, a blank actually counts as one. Blank actually counts as one. Beautiful. What about H2O? How many big circles, molecules of H2O do we see? Only count up the big circles now. Yeah, we see one here and we see two here. So we should put a big 2 in front of H2O. Again, if you multiply this out, 2 times 2 would give us 4 hydrogens. 2 times 1 would give us 2 oxygens. But again, you don't need to worry about the multiplication. Just know that that's what's really happening here. All right? So this is going to be our final equation. 2H2 plus O2 gives us 2H2O. Smiley faces emojis if you're feeling comfortable with that so far. Again, these molecules can change, right? We have 2 molecules and 1 molecule, so 3 molecules on the left, 2 molecules on the right. That doesn't matter. What matters is that when we balance the molecules, the individual atoms are matching up. Cool beans. All right, let's go ahead. I'm going to have you go ahead and do the next one. It's the exact same question. So you're going to see the exact same picture, and you're going to go ahead and on the whiteboard do the exact same question to double check that we really understand how to get coefficients from the big circles. Here we go.
Each circle is a whole molecule. Based on our drawing, which of the following is the correctly balanced? We just did that. So again, we're looking at the whole molecule. How many whole molecules, starting atoms here, and obviously these are ending atoms here. Okay. Using your whiteboard tools, I want you to box, circle, whatever, what you think we have here in that is a correctly balanced equation. Go, go, go. Good. Thank you, Shelves. I see you in the chat box. Excellent. I'm seeing some people popping up. Excellent. Nice job, Camilla. May Lynn's up on the board. Beautiful. I'm seeing some people in the chat box. Good. Excellent. Excellent. Good, good, good. I'm going to go ahead and put our whiteboard tools on hold. Again, we just did this. We just practiced this. But yes, I do agree with you. It is D. We have 2 molecules here of H2. Okay, 2 molecules. 1, 2. Let me get my pointer. 1. Oh, come on, tools. 1, 2. We have 1 molecule of the O's, of the O2s. And then obviously we have 2 molecules of the H2. 1, 2, 1, 2. So excellent job there. Let me go ahead. And this will be the answer for number 4 in your notes. I'm going to give you about 20 seconds. It is a multiple choice, so make sure that you are reading them carefully. They may be scrambled, so raise your hand when you are finished with number 4. Go, go, go. 20 seconds. Go, go, go. Stop. All right, there you go. Aria, Christopher, Omar, Tan, Jaden, and Dion. Thank you. So Gabriel, I know you're in the chat box. So Jaden and Dion. Raise your hands. Raise your hand, Jaden and Dion. All right, I will be checking Jaden. Last call, Jaden. We have been calling you and no response in the chat box. Jaden. Last call. All right, Jaden. All right, here we go.
Perfect. All right, let's go ahead and try our next one. So this is going to be a combustion reaction. And combustion, anytime we have combustion, we have a fuel that reacts with oxygen to produce fire, my favorite. So it produces carbon dioxide, it produces water, and heat in the form of fire. That's always a combustion reaction. The only change is you might have a different fuel. In this case, we have methane, right? In other cases, you might have propane or something else, okay? So let's go ahead and fill in how do we write out the complete molecule. So CH4, again, this C counts as its own atom, and there's no subscript, so that just counts as 1. How do I write out CH4 completely with no numbers? How do I write out CH4 with no numbers? Go ahead and tell me in the chat box. All right, so you have all the H's, Gabriel, but we also need that carbon. Don't forget the carbon. Thank you, Annabelle. Shelves, make sure you have all your H's. Keep on going, everybody. Thank you, Malin. Yeah, so we have one carbon, four H's. So yes, to write this out, I would get CHHH. H. All right, how do you write out O2? We already know this one, but let's keep on practicing it. Doesn't hurt to get more practice. How do we write out O2? Yep, two O's, so that's going to be OO. How do you write out CO2? Again, C by itself has one. A blank means one, and O has a 2 on it. So how do I write this one out? CO2. Thank you. Yes, this will be one carbon, two oxygens, so cool. And then H2O, how do we write that one out? We already know this one. Really, Shelves? That's funny. Yeah, again, this 2 goes with the H. And again, the oxygen doesn't have a number, so it just counts as 1. So 2 hydrogens, 1 oxygen, that'll be an HO. Let's count up the individual atoms on the reactant side, on the left side. How many carbons do you see on the left? How many carbons do you see on the left? 1. How many hydrogens do you see on the left? How many hydrogens do you see on the left? Yep, you should see 4. Perfect. And how many oxygens do you see on the left? How many oxygens do you see on the left? On the reactants. Yep, 2. Perfect. All right, moving over to the right-hand side. How many carbons do you see on the right-hand side? Yep, individual carbon atoms, we have 1. How many individual hydrogens do you see on the right-hand side? Yep, be careful. There's only 2 on the right-hand side. And how many oxygens do you see on the right? Now, oxygen is in both CO2 and H2O, so be careful. You got to count up all the O's. All the O's, yes, you should end up with 3 on the right. All right, so let's go ahead, take a look here. Carbon is fine, but we do need to balance hydrogen. Which side needs more hydrogen, the left side or the right side? The reactants on the left or the products on the right? Yeah, the right side needs more hydrogen. So again, I can only add molecules I already have. So in order to get more hydrogen, do I add another CO2 or another H2O? If I need more hydrogen, which of my molecules has the hydrogen I need? CO2 or H2O? I need more hydrogen. Need more hydrogen. I see Shelbs, I see Anthony, Stephen, Camilla. Yeah, I'm going to add another H2O. Perfect. So let's go ahead and drop that in here. We'll add another HHO. And recounting all the stuff we just added, how many H's do I now have on the right? How many H's do I now have on the right? Yep, now we have 4 in total because we have 2 on the top water, 2 on the bottom water. And how many oxygens do we now have overall? Again, I did actually add another oxygen here. So how many do we have now have on the right? Yeah, exactly, Shelves. Now we have too much oxygen on the right. So where do I need to add more oxygen? The left reactant side or the right product side? Which side do we need to add more oxygen to now? Yeah, the left. All right, so I need more oxygen. I can only add molecules I have. Do I add more CH4 or more O2? Do I add more CH4 or more O2? Yeah, let's go ahead and add more O2. Again, we can't just add O by itself. All right, we have to add the entire O2. All right, you can't just magically add oxygens by themselves. You can only add a whole molecule of O2. So now, how many oxygens do we now have on the left with these extra oxygens? Count up all of them. How many do we have on the left? Yeah, now we have 4 on the left. Is this balanced? Are my atoms, my individual atoms, now balanced? Yes. So we're not done though. We still got to do the equation. Now we're going to go ahead and give you a chance on the next slide to actually try to figure out the coefficients yourself, because again, on the third one, you have to be able to do it by yourself. So this one, again, when we find the coefficients come from the big circles, the big molecules. So again, you're going to count up the big circles that you see of CH4, of O2, of CO2, and of H2O to find the newest coefficients. Smiley faces, emojis if that makes sense, and then we're going to go ahead and give you a chance to actually try it out. All right, let's go ahead and practice it. Here we go.
Following is correctly balanced. We have just did this. We've kind of figured out all the individual molecules. So let our individual atoms, actually molecules. And here we go. So looking at the big one here, your whiteboard tools are, we have this one big one. We have a second one over here. So let's go ahead and I'm just going to see what comes up. Remember, we're looking at the big circles. The coefficients will be the big circles. Good. I'm seeing answers popping up on the whiteboard. I'm seeing answers popping up in the chat box. Beautiful. Excellent job. Nice, nice, nice. All right, let's go ahead. I'm going to go ahead and put our whiteboard tools on hold. Beautiful. Nice participation, everybody. So yeah, I agree with you. B is the correct answer. If you look here, this big circle, that is 1. We don't put anything in front of this molecule, again, because it represents 1. We look over here, we have 2 O2s. Okay, 1, 2, 1, 2. Right here, we have 1 chu. Okay, we have 1 chu or ku, ku, and then we have 2 H2s. Okay, 2 H2s. Excellent job. This is the answer to number 5. I'm giving you 20 seconds to go ahead and lock your answers in and go ahead and raise your hand. Go, go, go. Oh, guys, stop it, stop. Patrick, Angelo, Christopher, let's go ahead and raise our hands. Thank you, thank you, thank you. May, thank you. Michael and Alan. Michael, Alan, and May. Thank you, thank you. So just last call. Michael, 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 last call. All right, thank you so much.
All right, so this is an experiment using methane. Again, in our project that we're starting on Thursday, you will get a chance to choose from some different awesome reactions, one of which is methane. You've done this before, Ame? Yeah. So my husband and I did this experiment like 10 years ago when we first started teaching, so we look like little babies here. But what you can do is you can take methane gas and you can actually bubble it through soapy water. And that soapy water you can then put in your hand and you can light it on fire and it looks like you're fire bending. Now, before you put your hands into the soapy water, you actually wet your hands with water. And then you pick up the bubbles and then you light it on fire. Because first off, the fire goes up. And so that prevents it from going into your hand. And second off, water is an insulating substance, so it prevents any extra heat from getting on your hand for the moment that it's lit on fire. But it's super awesome. Unfortunately, I don't have a video of it. It does kind of look like a pickle. I don't have a video of it from when we did it, but I do have a video of Mythbusters doing it. So let's go ahead and watch them really fast.
Some homemade magic of their own. First out of the blocks is Adam, and he's intending to set the World Wide Web alight with a towering inferno of soapy water.
We're trying something an old friend of mine gave me, which is that if you bubble methane up through soapy water, you'll end up with a column of bubbles. Because the methane's lighter than air, it helps lift the column and keep it stable. And then when that column gets a certain height, however high you want it, you can light it and the whole thing goes whoom in flame.
And with a garden sprinkler on the end of a methane hose in a bucket of foamy water, it's not long before he has his very own bust of bubble.
I have been a bubble sculptor for about 20 years. The bubbles are a very fine way to sculpt the real world.
Their first attempt is a little lopsided, but Adam is poised to feed the fire of his pyromania.
That is.
All right, give me a smiley face emoji in the chat box if that's awesome to you, as it is to me. I enjoyed the fire, so yeah, don't do that on your own. But again, if you do ever get a chance to be in an actual chemistry classroom, you should ask the teacher if you can try that out with supervision. All right, looking good. So this last one, we're going to go ahead and do the diagram together, and then you'll quickly be able to just go ahead and answer the coefficients on your own for question number 6. So this is going to be the last question. This last one, you need to get the coefficients on your own. So, okay, go to the bathroom. So iron is going to react with oxygen to form iron oxide, which is known as rust. Just so you know, when we have a little letter next to a big letter, that actually counts as one whole atom. Remember, that counts as the same atom. So Fe is iron. So I already kind of filled this in for us. So Fe, we have one atom of Fe, we have 2 atoms of oxygen, and in iron oxide there are 2 Fe's and 3 O's. Smiley faces emojis if that makes sense. Again, I already kind of filled that one in for us. Okay. All right, so let's go ahead and count it up. How many irons do you see on the left? Again, an iron counts as Fe together. How many irons do you see on the left? Perfect. Yeah, we should see 1 iron on the left. How many oxygens on the left? How many individual O's on the left? Perfect. Yep, we should see 2. Perfect. And how many irons on the right? Fe's. How many irons on the right? Yep, we see 2. And how many oxygens on the right? Yeah, we see 3. Perfect. All right, awesome. So let's go ahead and take a look then. So Fe, all right, needs to be balanced. So I need more Fe's on the left, so what should I add more of? Should I add another Fe or another O2? Another Fe or another O2? Again, we can only add the circles of what we have. Yeah, so I'm going to go ahead and add another Fe. Obviously, adding another O2 wouldn't help me with my Fe's right now, with my irons. All right, so that looks good. So now I have 2 on the left. And that looks good. Let's go ahead and take a look at oxygen, though. I have 2 on the left, 3 on the right. Which side needs more oxygen? Yep, all right, the left-hand side, perfect. All right, so I'm going to add another O2 on the left because that's the only molecule that has oxygen. So here we go. Now how many oxygens do we have on the left? Now how many oxygens do we have on the left? Yeah, now we have 4. Are we balanced? Yes or no? Are we balanced? Yes or no? No. So we need to go ahead and fix the other side. So on the other side, we need more oxygen again. The only molecule I have is Fe2O3. So I'm going to add a whole Fe2O3, which is crazy, but that's what we got to add. Sorry, we're going to go ahead and add FeOOO. All right, now how many irons do I have on the right-hand side? How many irons do I have on the right-hand side now? Count up all those Fe's. Yeah, we actually have 4 now on the right because we added 2 more. And how many oxygens do we have on the right? How many oxygens do we have on the right? Yeah, we have 6. Are we balanced? Are we balanced? No! Oh my goodness. Let's go back to the other side. Okay, so on the other side, how many more circles of Fe do I need? Let's just go ahead. We have 2 on the left, 4 on the right. So how many more do I need on the left of Fe? Yeah, I need 2 more Fe's. So I'm just going to go ahead and add 2 more. I'm not going to do it one at a time. Might as well just add both of them at the same time. So here's Fe right here, and then here's Fe right here. Perfect. And now I have 4 irons, so that looks good. And I also need more oxygen. So what do I add more of to get more oxygen on the reactant side? What do I add more of on the reactant side? Why are you giving me numbers? Don't just copy other people. Yeah, we need another O2. That's what I was at, another O2. Yeah, so I'm going to go ahead and in here put an OO. Sorry, let me grab it here, right here. OO. All right, and now how many oxygens do I have on the left? How many oxygens do I now have on the left? Yep, now we have 6. Are the atoms now balanced? Are the atoms now balanced? Perfect. All right, so this last question, all right, you need to be able to figure out what the molecules are, what the coefficients are. Again, to figure out the coefficients, you need to count up the big circles, the big molecules. Here we go.
Of our Fe, take a look at our O's here, and then take a look at our FeOs on this side, okay? If you want to check in with us on the question and answers box. Please do not put any answers into the main room. Do not put any answers in the main room. We're going to give you just about 25 seconds. 25 seconds. Here we go. Go, go, go. Chat the question and answers box we're getting to, so no worries there. Let's go ahead and just check in with a few people over here. So looking for Tim, Aria, Ara, Patrick, Kale, Angelo, Christopher, Camila, Anthony, Eric, Omar, and let's see, Tayan. Sorry, things keep moving on me. Sorry about that. Tayan, Omar, Anthony, Christopher, Angelo, Kale, Aria, and Tim. Tim. All right, let's go ahead and keep moving. Let's keep moving. Awesome. All right, here we go. So we talked about defining reactants, products, and coefficients as in a chemical equation. We balanced a couple, and then we did this all through our 4B notes. With that being said, let's go ahead